Today we are going to discuss the topic problem decomposition to make the solution simpler. At the end of this session, you as students will be able to demonstrate various methods to decompose problems and make solutions simpler. There are various methods involved to make solutions simpler. They are the goal trees, Aostar, rule-based systems, rate networks, and many others. We talk about the goal trees being a form of mind mapping that helps to visually break down a large goal into smaller sub-goals and which must be achieved first before the global sub-goal is achieved. A large goal is sequentially broken down into smaller and smaller sub-goals until an elementary task is revealed, which cannot be further divided. Elementary tasks are cornerstones of a goal tree in a logical thinking process that is linked to the theory of constraints. It can be described as a tool to outline all the necessary components to achieve these particular goals. These goals are based on objectives called as critical success factors, to which we check for necessary conditions, which are called as NCs. How to break down now these goals into steps or simpler systems? So you define your goal, you determine what you want or what is needed to be done to accomplish your particular goal. Then you divide your task into high-level sub-goals. You may have n number of sub-goals. You break the first sub-goal into simpler, actionable steps, and then you plan when to do the first step and how long you are going to be with the first step before you select the second step. Then you go for execution of all these previous steps and then repeat and adjust as required and needed for generating your solution in mind. The goal trees graphically look like this, where a main goal is divided into sub-goals, the sub-goals into sub-sub-goals until you reach elementary goals. The next method is the Aostar, where this AND O star has certain basics associated with it. Here, rather than using two lists, open and closed, which we used in the A-star algorithm, Aostar uses a single structure graph, which represents part of the search graph and which was generated so far. Each node in the graph will point to the immediate successors and predecessors. Each node has an association with the h dash value, the estimate of the cost of the path, from itself to the set of the solution nodes. Therefore, G is not stored, that is, the path that takes you from the start to the current state in which the system is, as it is stored in the A-star algorithm. It is not possible now to compute the higher single values, such values which are there because there are many paths to the same state. Therefore, H dash now serves as the estimate of the goodness of a node. This Aostar algorithm goes with the first step being letting a graph that consists only of the nodes representing the initial state, and we call this as init. Now it contains only the initial state and we compute now H dash. That is, from this initial state to the goal state, what is the heuristic value? Now until the unit is labeled, we keep on solving it till the init h dash value becomes greater than futility, a value associated for terminating your algorithm, and repeat the following procedure. Trace the label arcs from init and select the expansion 1 of that which is not yet expanded nodes and occur in this path, and call the selected node as capital node. Generate the successor node. If there are none, then assign a futility value h dash to the node. If they are successors, then for each of them that is not also ancestor of the node do the following. Add a successor to the graph. If the successor is a terminating node, that is an elementary node, label it as solved and assign it a h dash value to be 0. If the successor is not a terminal node, then compute it as its h dash value. Now you propagate the newly discovered information up to the graph by doing the following. Let S be the set of nodes that have been labeled as solved and h dash values have been changed and need to propagate back to their parents. Initialize now S to the node. Until S is empty, repeat the following procedure. If possible, select from S a node of whose descendants in the graph occurs in S. If there is no such node, select any nodes from S, call this node as current and remove it from S. Now compute the cost of each of the arcs emerging from the current, and the cost of each are equal to the sum of h dash values for each of the nodes at the end of the arc plus the cost of the arc itself. Assign the current's new h dash value and minimum of the cost just computed for the arcs emerging from it. Mark the best path of the current by marking the arcs that had been at minimal cost and compute the previous step. Mark now the current solved of all the nodes connected to it through the new labeled arcs have been labeled solved. If the current has been labeled solved, or if the cost of the current was just changed, then it is having a new status and which must be propagated back to the graph. All that ancestors of the current to S. The remarkable points observed in the Aostar algorithm are the ancestors of the node whose cost was altered are added to the set of nodes whose cost must also be revised. The algorithm will insert all the nodes ancestors into the set, and this may result in the propagation of the cost change backup. Regarding termination of the backup cost propagation, since the graph may contain cycles, no guarantee is there that this process will terminate since it reaches the top of the graph. It turns out that the process can be guaranteed to terminate for a different reason. We then go to the next methodology which is adopted, which is called as a rule-based system. A system designed to achieve the artificial intelligence via a model solely based on predetermined rules which are defined. The makeup of the simple system comprises a set of human-coded rules that result in predefined outcomes. In the rule-based architecture, the condition action pairs, because everything is in the if-then form. So if a condition, then an action pair is propagated and represented as rules, and in this premises of the rules, the if part corresponds to the condition and the conclusion part corresponds to the action that has to be performed. A case-specific data is kept in the working memory, and if there are goals for finding the regularities in the data, then they can be expressed in the form of if-then rules. A rule-based expert system has 5 components: a knowledge base, a database, a reference engine, an explanation facility, and a user interface. All these 5 components generate the goal of this rule-based system. A matching rule captures the design decisions of the matching process the experts would take, and this is used to describe the knowledge-based rules to solve the problem. The main aim of the expert system is to take knowledge from the human expert, convert it into a number of hard-coded rules, apply it to the rule-based system, and then, since this input data is applied, we could generate a goal for this particular environment. The next methodology used to generate sub-goals and further simpler solutions is the Rete network. The Rete algorithm is a pattern matching algorithm for implementing rule-based systems. The Rete network is the heart of the Rete algorithm. It is made up of nodes that each node holds a list of objects that satisfy the associated conditions. The original Rete algorithm worked out for the facts, but we will simply specify the description to refer to objects, since all commercial engines have evolved to be object oriented nowadays. The Rete network is constructed when you compile a rule project only once and you have started the service for a class of simpler designs, and then it is shared across all invocations. A discrimination tree is adopted and built in the first part of the array network. It starts with alpha nodes that are associated with the class in the object-oriented sense. Here, this pseudo alpha nodes will generate further nodes, and all instances of the given class will be listed in any given alpha node. The discrimination happens by adding conditions as single nodes attached to the alpha node or another parent node. For our references, we have used. Thank you.